Welcome back my dear friends, a very good morning, good afternoon, good evening to all of you wherever you are in this part of the globe. And as you know, this is the DADM 3 which is data analysis and decision making 3 course under NPTEL MOOC series. And as you can see from the slide, this is the 13th lecture which is we are in the third week, third class in the third week. And this total course is for total contact hours is 30 hours, which when converted into number of lectures is 60, because each lecture is for half an hour, and the total duration of the week is 12 weeks. Now, this and as you know that each week we have 5 lectures, and after each 5 lecture we have one assignment. So, you have already completed one assignment, 2 assignments sorry, after week 1 and week 2, and after 12 assignments after each total 12 weeks you will basically be taking the final examination. So, if you remember, I was discussing yesterday in a very simplistic way that given an optimization problem, whether maxima, minima, and the dimensions were such that you can basically utilize the Cartesian coordinate to draw it. You can basically first draw the feasible region, which is basically the bounded area corresponding to the constraints which you have, and also remember that in the linear programming case you will have one of the two of the constraints, considering is a 2 dimension problem, that x 1 would be greater than 0 and x 2 would be greater than 0, greater than equal to 0. And in higher dimensions, if you have more than 2 variables like x 3, x 4, x 5, all of them would be restricted by the fact that all of these decision variables should be greater than 0. Now, again one thing I am repeating time and again here, that when you are solving a linear programming problem, there would be instances where the actual problem would give you, actually in practical sense the value should be integers, but we are not going to consider that when you are going to solve the linear programming problem. That will only come up in the case when you solve the integer programming problem. And point 1. Point number 2 is that I also mentioned that when you are solving the linear programming problem, considering the feasible region, actually if you want to find out the objective function and each and every feasible point, there would be infinite such feasible points. So, hence the total number of objective function to be solved would be infinite in number, but considering the simple concept of the corner point solutions, you will only consider your feasible search to be the corner points. So, in the problem which we solved, if you remember, I am not going to draw it, I am just going to mention it. So, you had the points A, B, C, D, and D was the basically the origin, A was the point where it was on the x on the y axis, and C was the point which was on the x axis. And we found out that the objective function as it moves outside and basically leaves the feasible region. So, that point is basically the maximum point, considering is an optimization problem which is a maximization one. In the case is a minimization one, obviously you will move more towards the 0, hence you will basically leave the space when you want to solve the problem. So, the point at which the minimum value occurs when the objective function leaves the feasible region would be the minimization problem. So, in the problem, sorry 1 minute. So, in the problem which we solved, the minimization problem would have been true when the objective function left the point D, which was the origin. So, but obviously there would be points also when we consider the feasible region where which would be non-zero, corresponding to the fact the origin is not the point when the minimization occurs. Point 1. Point number 2, also I mentioned that the general concept of trying to solve the problem would be that you start at any one point out of this A, B, C, D. So, it is very easy to visualize. So, if you start at the point D, you will basically take the direction to move in the case if it is an optimization problem, whether maximum minimum, to find out at in which direction the rate of change of the objective function with the rate of change of any individual decision variable is happening as the highest rate or the lowest rate, depending on whether it is an optimization problem to maximize or minimize. Now, this search technique will be utilized. Point 1, this is point number 2. Point number 3 also is that I very fleetingly mentioned that when you are trying to solve the problem, you will try to use the simple concept of Gauss Jordan matrix solution method, where you will be tempted to utilize the Gauss Jordan method such that the overall solution when you solve the problem will give you the actual answer based on which you can comment whether the optimization problem has been reached, whether it is the maximum minima. Now, the optimization problem would be reached based on the fact that when you are solving the maximization problem for the last example, the point B was the case when the objective function was taking the maximum value. So, any directional movement from point B either to point A or to point C, whichever direction it is, you will find out the rate of change of the objective function would be such that the objective function will decrease. So, hence you have to basically stop at the point of B, and that will also come out in the problem when you are going to solve. Okay. Another thing, in the last example we considered, the concept of shadow prices was the fact that one unit change in the constraints. So, there can be more than two constraints, and I told you that for the problem the constraint in the decision variables would basically be changed depending on how you are thinking about the problem, and this concept of trying to pick up the idea of which variables to consider and which variables not to consider would basically come from your experience. So, when you are trying to basically increase or decrease, the decrease part I did not consider. When you want to increase or decrease the constraint either for machine 1 or for machine 2, you found out that the feasible region obviously would change. Hence, your search space would also expand or contract, but the corner points in this case it would basically remain the 4 points. So, in this case we have basically renamed that with a suffix 1 or 2 or 1 and 2 depending on whether we are changing both the constraint 1 and 2, and this idea would be extended for the higher dimension also. So, let us basically proceed the problem. So, the range of the limit of machine 1 capacity for which the shadow price or the dual price remains the same would be the case when the value of M1, which is the machine 1 corresponding to the fact that it is 0 and 8. So, 0 and 8 would basically be the value of 0 would be for x1, 8 would be for x2. So, if you put that in the constraint 1, it will basically be 16. So, in that case that whole overall utilization of the machine 1 is being done in the proper manner. Now, when the value of when we take the value of x 2 as 0 and x 1 as a non-zero value, that means, if I consider the x axis and y axis. So, I am considering this is the constraint 1. So, this value is corresponding the fact. So, these are the two values. So, in one case if it is x 1, so this is 2.67 and 0, this value is 0 and 8. So, the constraints would be such that the values of the utilization of machine 1 would basically dictate that what is the utilization actually as per the norm, the total utilization which you have. So, when I consider the value of machine 1 and machine 2, so let me go back to the slide. So, it will be easy for me to explain. So, it is M1. So, I will write down M1 and M2 also. So, it is 2 x 1 plus x 2 is less than 8. I will come back to equation 2 also. So, 2 x 1 plus x 2 is less than equal to 8. So, this is 2 x 1 . So, when we put x 1 as 0, x 2 basically becomes 8. So, the overall utilization would be such that your points are 0 and 8, and this 2.67, let me go back. So, if you solve this equation, so you will get a value which is corresponding to 2.67. So, hence so this is the minimum utilization which you will get from machine 1. So, maximum utilization for machine 1 is 60, minimum utilization from machine 1 is 2.67. So, the overall capacity utilization if I consider, in one case it will be 2.67 by 8 percentage and another case it will be 8 by 8 percentage. In one case it is 100 as it is here, another case is less than 100. So, hence the range of utilization or capacity utilization for machine 1, considering that 8 hours is the case which has been given and constraint 1, is between 2.67 and 16. Now, when I go to machine number 2, so let me bring down machine number 2. So, it is x 1 plus 3 x 2 is less than or equal to 8, x 1 plus . So, in this case if I am able to utilize the whole capacity of M2. So, in this case the overall capacity maximum and minimum would be given for machine number 2 or the constraint 2, such that we know the range of limitation of machine 1 depending on the shadow price and the dual price, considering that they remain on the same value. Now, consider the value of the optimization problem as the ranges are changing. So, when you will be considering the range change, so you will basically consider that either the value, consider the, it is like this, you consider your objective function and the decision variables x 1 and x 2 to be the point at which you have obtained the optimum values, which is this. Now, let me use a different color. So, this constraint was initially true, this one was also true. Now, consider that you want to achieve the same value, but you want to basically change the combination of the x 1 and x 2 such that you obtain that values of x 1 and x 2, obtain the same objective function. So, what you do is that in point case 1, if it is, so I am just basically putting this pointer parallel to the blue line. So, what can be done is that I can either rotate it clockwise with the point of rotation being point number. So, this was basically B. So, that was the original one, it will keep rotating on the clockwise direction. So, what is happening is the utilization of product 1, which is x 1, would start decreasing, while the utilization of product 2, which is x 2, will start increasing, keeping in mind that the constraint remains the same, point 1. Point number 2 is the, and it will, I will continue to what range it is feasible. So, the range of feasibility will be till what point it basically touches that value which is along the y axis. Now, for constraint 2 again, which is the red line, where which is just below the pen which I am just placing it on the slide. So, again I can rotate it anti-clockwise or clockwise depending on whether you want to basically increase or decrease x 1. So, any increase and decrease of x 1 or x 2 would be such that the overall objective function remains same, the value of the x 1 and x 2 remains same, but to what range they are feasible, that will basically come out to what degrees of rotation is possible. Degrees means possibility, means to which level they are feasible, it will be true. Now, remember one thing, as you do that, the feasible region will also change overall, but the overall fact remains the feasible set, the actual values or optimal set where you will do the search, considering the corner points remain the same, are fixed. Fixed means not in values, but the numbers are fixed. So, say for example, if I keep rotating the blue line clockwise, so which means the point of where it cuts or it touches the x axis, which is x 1, and touches the y axis, which is x 2, would keep changing. So, hence the values of A increases, values of B remains the same, values of C decreases while value of D again remains the same. So, the overall feasible region changes, but the corner points basically changes corresponding to the fact that point O, but D and B remains fixed. So, when I am basically able to find that, that will give me the range based on which, or the ratios based on which I can find. So, the ratios which will be utilized to find out the values of x 1 and x 2 would be, or giving the shadow prices, I will basically calculate using the values of C 1 and C 2 would be given between the range of 1/3 and 2 by 1. That means, that is what is the ratios per unit range, unit values which x 1 and x 2 basically change, keeping in mind the constraint and the objective function. Now, in the case if I fix C 2, the rate of change of the function for product 2 correspondingly, then the values of C 1 range are between 1 by 3 to 4, such that it will give me the values of the maximum, the minimum profit which can be obtained. Similarly, for the fact when I want to change C 2 keeping C 1 fixed, the values are 3 by 2, which is 1.5 to 9. And in the higher dimension, obviously, if it becomes that you will have many such many such planes which are the hyperplanes will be rotated in different directions corresponding to the fact that the change in x 1, x 2 or x 3, x 4 depending on how many whatever the dimensions are would give you the values, how you basically find out the solution. Now, the questions would arise. So, if this company can increase the capacity of both the machines, so which machine should it prefer? So, obviously, the question in a very layman terms would be, it would prefer the machine where the increase of unit cost or the total cost for producing product x 1 and x 2 is the least out of these two constraints, because there are two machines, and the corresponding increase in the objective function is also maximum. What we will consider is that objective function value is increasing, cost is also increasing. So, I will basically make a compromise that the rate of change per unit increase in the cost, what is the per unit additional in the objective function value in the positive sense. So, we will basically take that machine to be true. So, in this case we have two machines. So, we will only consider two values in order to make the comparison. We will also consider, is it advised to increase the capacities of machine 1 and 2 at the cost of $1 per hour. So, that will basically mean that as the constraints increases, as they shift more towards away from origin and more into the quadrant 1, both for constraint 1 and constraint 2, considering the objective function is a maximization problem, we will basically try to find out that how does the value of B change. So, in one case, if only constraint 1 is changing, B changes to B 1, if only constraint 2 is changing, in that case B changes to basically B 2, if you have seen that, and if both of them are changing by 1 unit, it will be basically be changing, B is changing from B suffix 1 and 2, which I had basically shown in the last day. So, we will basically consider that how it can be done. If the capacity of the machine will increase from 8 hours to 13 hours, how it will impact the revenue. So, if the capacity is changing, that means both the constraint which is machine 1 and machine 2 will shift parallelly by 5 units. So, constraint 1 will also shift 5 units, constraint 2 will also shift 5 units, both of them change at the same quantum. So, in that case you will basically have different value of A, a different value of B, a different value of C, but the value of D will remain the same because that is the origin. So, we will basically try to find out that what is the objective function, considering that we have to now do the search at again at the 4 different corner points as the case is. Suppose considering the unit revenues of product 1 and product 2 are changed from 3.5 to 2.5. So, the corresponding values in the objective function and the constraints would also be its revenues are changing, that means it will have an impact on the objective function, so hence it can be considered accordingly and we can make the decision. So, now these questions we will try to answer. So, this general formulation will be considered here. So, let us consider a very, now we will basically try to solve it using the matrix multiplication. So, matrix or Gauss Jordan method or the matrix concept. So, here I will basically pause for 2 minutes and then give you the idea. So, let me, so I will come to this table later on. First a simple concept of actually let me make this slide beforehand. So, it will be easier for us to just that is great. Okay. Now, what does general solving of a linear equation mean? So, what we have is we have consider we have a x 1 so you have equation a x 1 plus b a 1 1 plus a 1 2 x 2 plus a 1 3 x 3 plus dot 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 plus a 1. So, this is the actual equation we will use and I will write it. So, a 1 n x n is equal to b 1. So, this equality need not be true, it can be less than greater than whatever it is. Second equation is a 2 1 x 1 plus a 2 2 x 2 plus a 2 3 x 3 a 2 n x n a let us consider is a m 1. So, m and n are not the same. Generally, if they are equal, then it is well and good, and we will try to make them equal for some reason. I will come to that later. Again the equality sign need not be true, less than, greater than, whatever. Now, look at this equation. So, that will remind. So, here I will be basically talking more of basic mathematics, which I am sure all of you know. Consider you have an equation 2 x 1 plus 3 x 2 is equal to 5, and in another case you have basically 5 x 1 plus 10 x 2 is equal to 10. So, what you will do? Use both the equation. I am not going to write it, I am going to basically write it when the actual part comes. So, you will use both the equations. First case you eliminate, multiply sum of the parameters for either equation 1 or equation 2, and then eliminate either x 1 and x 2, find out x 1 or x 2, utilize that x 1 and x 2, find out the other thing. So, given first we find out x 1, we find out x 2, then or else given x 2 we will find out x 1, and then just to double check we will plug them in both the equation, check whether the values are being satisfied for both equation 1 and equation 2. Now, when we solve the problem, it may be possible that one equation is the multiple of the other. Consider is x 1 plus 2 x 2 is equal to 4, and in another case you have 2 x 1 plus 4 x 2 is equal to 8, which means the second equation is basically being given by a convex combination of the first. So, which means that a number of such solutions which you will have for x 1 and x 2 to satisfy that equation would be infinite. Now, when we utilize this concept, we are aware that there is a concept of rank of a matrix. So, once we have this set of equation which is in front of you, which has basically a 1 1 to a 1 n in the first row, a 2 1 to a 2 n in the second row, a m 1 to a m n in the last row. So, you will basically have 1 2 3 4 till n this 1 minute. So, this will my mistake, wait, I think should be m 1 1 2 3, yes, sorry. So, they would be basically m rows and these would be technically n columns. So, if I consider, so we have m rows and n columns. Now, if you want to express that set of equations when you are solving a set of simultaneous linear equation, what we do? We write it as, I will use a different color. So, this black color and the red color will make, or whatever other color I am trying to utilize, that will make the idea much clearer. So, we use A, which is the matrix corresponding to the A values which you have. You have x, which is the vector, not the matrix, vector corresponding to the x values which you have, is equal to B, which is the vector corresponding to the B values which you have. Whether it is a column vector or a row vector, that would basically depend on the dimension of the problem. So, in this case, if A is basically of dimension m cross n, then in that case x would be n cross 1, such that the overall result which you will have by multiplying A and x would be m cross 1. So, m cross n would be for A, n cross 1 would be for x, and m cross 1 would be for B. So, how do we solve it? Using simple, very simple concept of matrix multiplication. What you actually do is that you either pre-multiply or post-multiply A by its inverse. So, if you pre-multiply and post-multiply, which we will consider by the concept that pre-multiplication by A minus or post-multiplication by A minus would give you the identity matrix which is I. So, as you keep doing that step by step, you also do the same thing on the right hand side. So, if you are pre-multiplying A by A minus, you will also pre-multiply B by B minus onto the left hand side. So, hence the end result which you will have would be this, which means the overall result of pre-multiplying A with A minus will give you the identity matrix. So, you will basically have I into x is equal to A inverse B. So, when you find out the actual values which are on the right hand side, they will give you x. So, what you are doing is that you are converting A step by step into identity matrix, and you do the same level of pre-multiplication, post-multiplication in the row and the column on the right hand side, which is on the equation, such that you basically get the values of x. So, this is the basic thing. You will basically have a starting matrix, and you will basically convert that A, and you will basically convert that into the I, which is the identity matrix, which will basically be the one along the principal diagonal, as you know. And as you are doing the same multiplication, same operations on that matrix, you will do the same thing on the right hand side. So, you will basically at the end of the day arrive at the value of x, which will give you the actual value that will give you the optimum solution. Now, as you are doing it, you are also doing the same thing to find out what is the objective function. So, at the end of the day, when basically A becomes I, the actual results will give you x along with the objective function which we intend to get. We will come to the problem later on and in the next class, and have a nice day, and thank you very much.